I'll say this for it's worth putting on video. So I think we have something in the grad classes, but something I don't know if it's well advertised or not, but you can take grad classes as an undergrad. I mean, right now it's probably not the best time, but once you have more prereqs and stuff and you're ready for that stuff, you can take up to 2. I hope this is still a thing. It was when I was a student. You can take up to 2 grad classes. You just have to fill out an extra form. So if there's some grad class that you're interested in, find that class, talk to probably Shelly, fill out the form, and then get into that class. I think it's very little advertised, but a very good benefit that you can have. Because there's some, especially when it comes to like security and a lot of AI stuff, and there's a lot of fun topics that we have a lot of good grad classes for, but not much in the undergrad level. All right, but let's get started. So we are on the state pattern. So we're in our last week of content, and this is AO only content. I know I've said this before, but I want to reiterate just to make sure we're all on the same page with this. The last application objective task is the state pattern task. It's like the ninth like programming task. And it is application objectives only. It's worth 2 application objectives, no learning objectives. So nobody has to complete this one to pass the class. Everybody, task 1 through 8, that's what you need to do to pass the class and the interviews and quizzes. Nobody needs to do this one, but there's 2 application objectives on the table. So also, if you already have your A or whatever your target grade is, you're not going to hurt my feelings if you don't take this one, if you don't do this assignment. So it is kind of optional, but there are points associated with it. The points work a little bit different. There's only one deadline for this task. It's due that last day of the night of the last day of classes, the same time all of the 8 tasks are due for that final deadline. And there's only one deadline, but there's still 2 application objectives associated with this one. So there are features broken down into 2 categories. So the basic features, testing and implementing these features, and then the advanced features. And these are worth 2 separate application objectives. So depending on how far you get in the assignment, you can get 1 or 2 application objectives. And I want to make sure I say this because it's different from every other assignment in the entire course, which I don't know, maybe I don't know how I would change that, but it's different because once you get your 1.0 in Autolab, that's not the end of it. There's still another application to be earned. You can see a 2.0 in Autolab. So you don't have this one all the way completed until you see that 2.0. You can get 1 application objective or 2 application objectives for this. And those are different scores in Autolab. Because there is no deadline, there's no expected deadline, expected, late, and final. There's just one deadline flat out, and it's however much you completed on the project before that deadline. So what the task is building a 4-function calculator. The calculator a lot of it is given to you. So this is a separate repo to clone. So like way back in task 1 where you clone the repo and then worked on all 8 tasks, this is a separate repo to clone. So make sure you go and get the starter code from this. And if we take just a short tour, there's these 3 packages in the calculator package. Controller and view. View is a GUI for the calculator. You'll actually have a calculator that comes up, and you'll have buttons you can press and a number that's displayed. And this controller package has a whole bunch of classes, which are very small classes. The view and controller packages you shouldn't touch at all. Don't change a single character of code in either of those. Those are all set up and given to you just to get the GUI working the way that we want it to. And then the model is where all of your code will go, aside from your tests in the test package, of course. But this is where all of your code will go. The calculator class is given to you to make sure we're on the same page with the structure of the project. And then you can add as many classes, sub-packages, anything you want in this model package. The calculator that's given to you has methods for all of the methods that the GUI is going to call, which mostly correlates to the buttons that will be pressed. You have a clear pressed clear pressed, number pressed, which takes an int of 0 through 9, what number was actually pressed, divide pressed, multiply pressed, subtract, add, equals, decimal. So whenever one of those buttons is pressed, it's going to call the corresponding pressed method in your calculator class, or an object of type calculator rather. And it's going to call this display number method, which should return whatever number should be displayed to the user. So these methods are what you want to implement to be able to get all of that behavior working. And as you implement these methods, of course, write your tests, but you can also fire up the GUI and press the buttons to see if it does what you expect it to do. Okay, the basic features, I'm not going to go through all of them, but explaining what the calculator should do. The basic features is mostly getting it to work to begin with. It has a 4-function calculator. If I hit 1 plus 2 equals, it should say 3. Pretty straightforward. Is building that functionality to begin with. And then the advanced functionality, adding things like pressing the decimal button to get floating point values, and hitting equal multiple times in a row to repeat the previous operation. There's also a lot of undefined behavior, and maybe I should put this undefined behavior at the top of the document, but undefined behavior is behavior that is not defined by the document. I guess that's pretty obvious. But and we've been talking about this throughout the semester, but it's got to be highlighted on this one because there's a lot of undefined behavior. Any of this behavior is not defined by this document, and the question becomes, what should the calculator do when these certain button sequences are pressed? For example, if I hit 2, 5, divide, and then star, and then times. So I have 2 operation buttons that are pressed sequentially. What should happen? And I'm going to say it's undefined. I don't know what should happen. You don't know what should happen. So I'm not going to test it. You're not going to test it. And we're going to pretend that this is an invalid sequence of button presses. So that's how we'll limit the scope of this project. I used to, there was at least one semester where all of this behavior was defined, because this one's pretty easy to define. I think this should be 125. It should do 25 times 5. The multiplication should override the division. I think that's pretty standard what the calculator should do. But just to limit the scope of this, because I had all this defined before. I played with a couple different calculators, saw what they all did, defined all the behavior, and said, code it all up. And it's just a lot. It's a lot, and it gets tedious. After you do what the assignment asks you to do, you'll get the point. You'll get what the state pattern is. You'll understand what's going on. And then the rest of it's just extra tedium, which I don't need to put you through. So you don't test it, I don't test it, and we'll pretend that these don't exist. That's all undefined. If you ever have failing a correct solution in AutoLab, and I look at your tests in office hours, and you have undefined behavior being tested, because you're like, well, that's what the calculator should do. That's why you're going to get that. If you're guessing what the expected behavior should do, if you write up a test case and there's nothing in this document that says this is what it should do, and you're guessing, that's undefined behavior that you're testing, which is not something you should ever do. Do not test undefined behavior. Within this class, of course, because I'm talking about it, but also throughout your career. You should never test, I shouldn't say never, I don't want to say it that strong, but you shouldn't be testing undefined behavior. Out there in the real world, what you would do if you're inclined to write a test for undefined behavior is you would get together with your team and say, hey, look, this is undefined behavior. What should the behavior be? Define it and then test it. That's really realistically what you should do in the real world. If you're testing undefined behavior, define the behavior. And a lot of times your test will define the behavior, but you got to make sure your whole team's on board with that. We can't really do that in an academic setting because once the homework's released, I'm not going to change it and start adding requirements to it every time somebody wants to test undefined behavior. So we are kind of stuck with what I release. I think there would be a lot more people upset if I keep changing homework documents after they're released and then updating the graders in AutoLab than having some undefined behavior existing in the homework document. So we'll just leave it undefined in class, but there's a lot of undefined behavior in this one. So I want to make sure I'm explicit about, hey, look, these are things that you could do on your calculator. We're not going to test these things. So just being more explicit than I usually am about it, just because there's so much of it. Okay, so that's the calculator. That's what we have to write. But What are the types of questions going to be asked for interview 3? I mean, I've been through 2 of these interviews. How am I still getting these questions? I guess I don't know exactly what you're asking. I'll try to give you something. What's it? Inheritance and polymorphism? I mean, just questions about those 2 weeks. Yeah, I'll just give a vague answer to this one. Just questions about those 2 weeks. Study what we went over in inheritance week and polymorphism week. And anything covered during those weeks is fair game. We'll try to. No, we can't really even do that. I was gonna say we'll try to focus on questions that weren't already covered in the quiz, but that's hard to do. We'll have to have some overlap there. Anything for graphs file reader? No. No, graphs is on task 8 only. Task 8 is the only time I'm assessing graphs. All right, so that's the calculator. This is what you have to code. I know I didn't go through all the details, but it's building a 4-function calculator where the GUI is already given for you, and you have to implement those methods and keep track of, as buttons are pressed, what should be happening. And let's be honest, it's a 115 project, right? You could do that at the end, but not really at the beginning, but at the end of 115, you could handle an assignment like this. So why am I giving it to you at the end of 116, a full semester later? And that's this condition right here. So you have to write everything for this assignment without using control flow. That's conditionals and loops are really the control flow that we have. So any of these keywords, if, else, which inherently includes it, else if, switch case, which is something we haven't talked about, but it's a different syntax for writing if, else if, else if, else if, else. It's a different syntax to be able to write that. Try, throw, catch, finally, any of these. We did a little bit of catching exceptions. You can use these to simulate conditionals, so those have to be banned as well. Any loops, for, while, and do well. I never really talk about do well, but it's a while loop that will always execute at least once. So do the loop block and then check the conditional at the end of the loop. So where a regular while or a for loop might never execute, not even once, a do well will always execute at least one single time. But otherwise, it's the same as a while loop. These can all be used to simulate conditionals also. I would prefer to allow loops for this assignment. They aren't really helpful for it, as it turns out. But I have to restrict them because you would use them to simulate conditionals. You can use them to simulate conditionals. For example, a while loop, right before your while loop, Boolean flag equals false. Well, whatever conditional I want, that would be my if statement conditional, or flag, and then at the end of your loop, flag equals false. Did I say that right? Or and flag equals true, and then flag equals false at the end of the loop. So that loop will execute exactly once. It's exactly an if statement, just with a little extra overhead that you have to do to make it an if statement. You can do the same thing with a for loop and do well. You can do the same things, but it would execute once, a little more work there. But you can use these loops to simulate conditionals, so those have to be banned. And anything that's against the spirit of the assignment is also banned. If I find anything in your submission that simulates a conditional, that's also banned and can't be used. And in general, this is conditionally executing your code. So if you have anything in your code that, based on the value of a variable or the evaluation of some Boolean expression, says if this certain set of circumstances, run this code that you wrote, otherwise run this code that you wrote, that's banned in this assignment. If it's based on the values of variables or a Boolean expression in general. One thing, there are creative ways to do this. One thing that, I don't think this came up this semester, did it? But shortcut evaluations, if you don't know what those are, don't worry about it because they're banned for this assignment. But if you do know what shortcut evaluations are, they're banned for this assignment. Don't use them if you're thinking, well, I can't use conditionals or loops, but I'm going to get creative with this. That's also banned. So your code can't run conditionally, any code that you write. And the reason I'm saying it like that, if you call like a Java method and inside that Java method it does use a conditional, that's perfectly fine. But it can't be your code that runs conditionally. Yep. Oh, cool. Can we use control flow in testing? No, including your tests. That one I would also like to allow, but we love our loops, Jesse. And in your tests, I would like to allow that too, but it's too hard to set up in Autolab in that somebody will hide functionality in their tests and then call that, I don't know. Maybe I could allow it someday, but maybe there's a way around that. But right now, what the autograder does is takes your submission and goes through all of your code and replaces any of these keywords with something that won't compile. It'll say redacted keyword with a bunch of asterisks. So any keywords are going to be replaced by that, and then your code doesn't compile. So the way that that's structured in your tests as well. Yeah, now I'm thinking about how would I change the grader? It'd be a big change to the grader. That'd be tough to do because then you'll name your project directory tests and then hope that my grader doesn't look in there for conditionals. Like, I mean, if you get caught, it'd still be, bad. But let's try to cover anything possible that a student might sneak conditionals in. Because if you're allowed to use conditionals, like I said, it's pretty trivial. This could be task 1. But without conditionals, it becomes significantly more difficult. I shouldn't say that, but without tasks, what am I talking about? Without conditionals, without control flow, the reason why I do this, and I'll say this sooner rather than later, just in case I forget, the reason why conditionals are banned is because it will force you to use the state pattern. And that's really what I want out of this assignment. I want you getting your hands on the state pattern, but if I don't force you to use it, you're not going to use it. Just like recursion, if I don't force y'all to use it, most of y'all for task 3 aren't using recursion. Like, unless I force you to use something like this, something new and unfamiliar, a lot of y'all won't use it. So that's the reason why control flow is banned, is to force you into the state pattern. I am not by any means saying that control flow is bad. You should use control flow. It's something you will use throughout your entire career, and you absolutely should. But banning it is just to push you into this new way of thinking, using this state pattern and using OOP and polymorphism and all that stuff that we've been talking about all semester. The state pattern is an application of OOP. You'll need to know references, objects, inheritance, and polymorphism, all of it, all the stuff we've been talking about with OOP all semester. You'll need to understand all of it to be able to apply this state pattern. But it isn't a brand new concept. We're not going to learn any new concepts here. It's just a combination and application of all of those concepts we've already learned. And that's why it's not a learning objective. That's why it's strictly an application objective. Because you already know all the stuff that you need to know to be able to do the state pattern, and you are literally applying it in a new way, application objective, which kind of got away with the spirit of application objectives in a lot of ways, but this way is strictly keeping to application objective. Can you apply what you learned in a brand new way? Oh, and in today's slides, I'm going to cover everything that is the state pattern today. Like realistically, maybe not realistically. Yeah, realistically. You could do the application objective task after today's lecture. You'll know everything you need about the state pattern. And then I'll do live coding Wednesday and Friday. Friday, I might go over, I have a project where I use the state pattern. I might go over that one. I haven't really decided yet. Whenever I do it in lecture, it's just so much that it gets a bit overwhelming. So what I like to do is start with a problem statement and then just live code from scratch using no control flow. Yeah, no control flow, using the state pattern. That keeps it a little more managed. Okay. The state pattern. The state pattern is a design pattern. It's the only design pattern I'm going to cover in lecture. But there are a lot more design patterns. If what we do with the state pattern seems interesting to you, design patterns is your search term, or the Gang of Four. They're the people, a group of people who came up with these design patterns. They're all consultants, who've worked with a lot of different software teams over the years. They all got together and said, hey, we see like the same problems cropping up constantly all over the place, specifically related to OOP. These are all OOP design patterns. These certain problems come up all the time, and a lot of these software teams, they've been coming up with these solutions, and they got together and said, hey, let's kind of standardize that, give these common solutions names, call them design patterns, then publish them out there for everybody to see to kind of save us time. Like when we come up with this certain problem, throw the design pattern at it and be able to move on more quickly. That was their goal with this. The state pattern is one of those design patterns. It's an application, as I mentioned, an application of polymorphism, which polymorphism, we need inheritance. Inheritance, we're going to need classes and objects. And if we're using classes and objects, at least, well, not even just in Java, but if we're using classes and objects, we need to understand references. All of those topics come back. So what the problem is that the state pattern is going to solve is when we have an object that wants to change its behavior based on a certain set of circumstances. It wants to change that behavior significantly and has quite a few different sets of behaviors that it can have. That's when the state pattern comes in and is helpful, I'll say. And to start, if we want to just change the behavior a little bit, it has to be a significant change of behavior. If we just want to change the behavior a little bit, we're probably going to do that through instance variables. We're going to change the values of the variables, and those values will determine the behavior and change the behavior in some way. If I want a character in a game to have more attack power, I'm going to increase some integer stored in an instance variable, and then just throw that into a formula, and that's going to change the behavior, but not significantly. It's just going to change it a little bit. So what if I want very different behavior from an object? Well, what I could do, if I don't want to do anything with the state pattern, is say if some Boolean expression, do something, exhibit some behavior, else have some completely different behavior. And I'm going to write different code for each set of behavior. It's going to be, can be as different as I could possibly want it. It's 2 different code blocks. It can be whatever I want. Very different behavior. And this is fine. And I want to make sure I get this out there. By no means, I already said that part, didn't I? By no means am I saying conditionals are bad. And this is a good approach for most problems. If you see this chunk of code anywhere in a project, you shouldn't be thinking, man, they should have used the state pattern there. What are they doing using a conditional? No, you should do this. In most cases, this is going to be the best way to do it. The state pattern is not one of those things where it's, now you know the state pattern, you should be using it everywhere. It's something with quite a bit of trade-offs. It's something that has a bit of trade-offs. It's not just an overall good thing. Like when we first teach you conditionals, we're like, these are conditionals. You're going to use them every day. Every day that you code, you're going to be using these things. State pattern is not like that. You might never use the state pattern in your career, but armed with the state pattern and knowledge of the state pattern, being able to look at a problem when it comes up and decide, would it be better for me to use the state pattern here, or should I just throw some conditionals at it and some control flow and be done with it? And a lot of times you're going to choose the control flow, and you should. But there are certain situations where the state pattern is going to be beneficial, where you can gain from it. And I want to talk about what those situations are. But if I didn't make it clear enough, by no means is, oh, I know the state pattern, I'm never going to use a conditional again. No. Because I've had that misconception a lot, just the way I present it. Banning control flow. No. But control flow is amazing. You should use it a lot, just not on this last task of the semester. Okay, so things get a little more dicey if we have a lot of different behavior. This is where the state pattern does start showing some of its benefits. And I know I haven't even introduced what the state pattern is. And just to preface this, I'm going to go over all of the definition of the state pattern with blocks of text and slides like this. It's going to be kind of boring. And then I'll do an example that will hopefully drive home what it is. And then Wednesday and Friday, we're doing live coding. But let me get all of the definition out of the way. And the motivation of why we would even do this. So if we have something like this in our code, we're like, I'm using conditionals for everything. And you start ending up with this. If, else if, else if, else if, else, and 5 completely different behaviors that one object can have, you got this statement in your code somewhere, and you have one function or one method or one object that has 5 different behaviors that it can have, this starts getting messy. When you start seeing code like this, you should start thinking of a way that you can refactor this and do something a bit better, a bit cleaner, because there's a few bad things about this. One, it's hard to read if you're going to go through this code where each behavior might be 10, 15 lines of code. Your conditionals can be fairly complex. They're going to have to be if they're controlling something like this. So it's going to be hard just to tell what this is doing when total it's going to be upwards of 100 lines of code for this one if statement. That's tough. Somebody coming on this team might have a harder time doing that. And hard to maintain. I use the word maintain quite a bit, but I'm using it in the same context as we have all semester with OOP. Really the big theme of OOP is making it easy to add new features. This is going to be hard to add a new feature. If I want some 6th behavior in here, I have to figure out where it's going to go in these conditionals, and then I have to change what those conditionals are, because there's certain sets of, thinking of the truth table of all these conditionals, there's certain sets of those truth values that used to go to a different behavior that are now going to the new behavior. And I have to be very careful how I write my conditionals to make sure I'm getting the right behavior in the right circumstances, and making sure if I want this behavior that none of the conditionals before it are going to be true. So I have to make sure I have some nice disjointness between these conditionals, which can get tough, difficult, tough to maintain depending on what they are. And making sure I didn't break anything. If I'm going in the middle of this and adding another else if, I have to make sure I didn't break any other behavior and different sets of behavior. When this method's called 8 times in a row with different states, I have to make sure I didn't break any of that. So retesting things gets tough when we're adding to a big mess of code like this. It's very difficult. Not to get too off track, but a lot of CSE 312 students have code that looks like this, and the homeworks build on each other, and they just add more else ifs in here. And they usually break old code when they add new features. And maybe I should go over a state pattern with them again. And I tell them the same thing every time. Well, your code is horribly organized, to put it nicely. When I'm feeling nice, I'll word it like that. But so let's try the state pattern. Let's learn what the state pattern is and throw the state pattern at this problem to give us a new tool in our toolbox. So instead of having one class that stores all of the behaviors, instead we're going to have that class or objects of that type defer to some state object for all of its behavior. We're going to create a different object depending on what set of behavior I want to have, and then defer to that object for functionality in a way that we're going to change the behavior based on the type of that object instead of changing behavior based on the value of variables. And this is going to be the crux of what the state pattern is, using polymorphism to change behavior instead of conditionals. So we're going to have a concrete state object for each different set of behavior we can have that are all going to extend, or in the code implement, a common interface. And then we're going to store a variable of the interface type. And then depending on what concrete object is stored in that variable, we're going to get different behavior because each type is going to have different implementations of that method. And we're just going to defer to that. So instead of having a bunch of conditionals and saying, if this set of conditionals do this, we're going to say, hey, state, just do it. And that state, depending on what type it is going to have a different implementation for that method. And what we end up with, what the trade-off is we're going to have more code, or not more code, more files, because each piece of behavior needs a separate class, and we have the interface. We're going to have more files. So if that's something you don't like, that's one of the trade-offs you're making. But each file, and especially each method, is going to be much, much smaller than it normally would be. Instead of having that one method that's 100 lines of code, you're going to have a bunch of methods that are each 15 to 20 lines of code. sticking with the numbers in my exam. Those numbers are just made up, by the way. So we have smaller pieces of functionality, but more of them. It's one of our big things. So somebody coming onto the project, they are going to have to click around quite a few files to figure out what the hell is going on, which might be something that you say, you know what, I don't like that, I'm not doing this. But each file will be easier to read. So definitely trade-offs. So to do this, we're going to have an abstract class. I'm actually going to have an interface in the code that I show that's going to find the API. API is a term that's pretty overused, and I happily overuse it also. But API, Application Programming Interface, is the way two pieces of code interact with each other. So we're going to have some interface that's going to define the API. This is all of the methods that can be called on the object that we're applying, that can have different behavior, that we're applying the state pattern to. For your calculator class, this is all the button press methods. That's the API. If I give an end user a calculator, that's what they can do to interact with it, is they can press the buttons, and they can read the number that's displayed on the display. That's the API, and that's given to you in the programming assignment. Then we're going to have a concrete class, so an abstract class that defines the API, and a concrete class for each different state that we can be in. So any different sets of behavior that we want to have in that object, we create a new concrete class, extend the abstract class that defines the API, or implement the interface, and implement all of the abstract methods in each state to get different sets of behavior depending on the type of the state, and then attach the state to the object and defer to that state for the behavior. Depending on its type, it'll get different behavior. And then also give a reference to the object that the state is attached to the state. That one's going to make more sense in the example when we start looking at code, so I'll save that conversation for when we have some code. I would ask for questions now, but there should be like 100 questions right now. Is there going to be a lot of hard coding? I don't know how to answer that one. For the programming tests, I wouldn't call it hard coding in the sense of like hard coding the values, like plus and numbers. I don't know how quite to answer that one. But so let's talk about what that all means. That's like the concept, the theory behind the state pattern. Let's get an example to make this make a bit more sense. And for that, I'm going to call on my buddy Bruce Banner here. He's going to help us figure this one out. Bruce Banner, I assume most of you know who this is, but just in case, he's a fictional character. He's a world-class scientist. We'll call him Dr. Banner at this point. He can drive a car, and he's not very helpful in a fight. But if you make Dr. Banner mad, he's going to turn into the Hulk. He's not going to be able to drive a car, but he's great in a fight, and he's a bit out of control. So this is one being or one person that can be in two very different states. So we're going to say this is Bruce Banner, who can either be in the Dr. Banner state or the Hulk state. Very, very different behavior, not just something we would change the value of a few variables to change the behavior, but completely different behavior depending on his current state. So let's simulate this. We're going to have the Bruce Banner class. I just said this. The Bruce Banner class, who will behave very differently depending on whether he's in the Dr. Banner or Hulk state. And we're going to define the API. I'm going to come up with 4 methods that are going to be the API for Bruce Banner. And that's make angry, calm down, use car, and fight. These are the API methods. And I'm going to create a state class. So an API of type state. And then for all 4 of those methods, the Bruce Banner class, which the parallel is your calculator class, is not going to implement much functionality at all. Bruce Banner is not going to have really any at all. Your calculator will have some. But instead, we're going to defer to the state for the functionality of each of these methods. So when somebody calls use car on a Bruce Banner is going to say, hey, state, we're going to use a car. And the initial state here is going to be of type Dr. Banner. So it'll be Dr. Banner's use car method. But if the state changes to the Hulk, use car is going to be the Hulk's use car method. So depending on the type stored in this variable, we're going to get different behavior. So I'm going to have a state interface, which is going to define the API. These are all of the methods for which I'm going to defer to the state for functionality, which in our cases here, it's going to be all 4 methods. All 4 methods are going to be deferred to the state. I'm going to create a concrete class for each state that Dr. Banner can be in. I'm going to implement the interface, and then implement all 4 of those methods. And once we have this set up, so the state pattern is very much so an architectural challenge. How are you going to architect your code? How are you going to design your code to be able to accomplish what we want, the calculator in the homework? And then once you set up the state pattern, once you have your code designed, actually writing the code should be the easy part. Should be very easy, in fact. When I'm going to write the code and I have everything set up, then the questions I'm asking myself are, when Bruce Banner is in the Dr. Banner class and somebody calms him down, what happens? It should be a very narrow focus, and each method you implement should be pretty easy to write given that focus. Bruce Banner is Dr. Banner and someone calms him down. I'm just simulating stuff so I can fit this stuff on the slide, but he's already calm, nothing's really going to happen. What if he's the Hulk and somebody makes him angry? He's already angry, nothing's really going to happen. What happens when he's the Hulk and he uses a car? He's just going to smash it. What happens when he's Dr. Banner and uses a car? Well, he's just going to drive normally. It's going to be fine. The car class, I'm not going to show on the slides, but it's in the repo if you're curious. It's a pretty boring class, a pretty boring object. And we have a bit of overhead. The extra complexity here is getting a reference to the object to which the state is attached. This is where we have a bit more going on. So whenever we create a new state object, we're going to pass that Bruce Banner reference to it so it knows the Bruce Banner that it's attached to. This code is going to be executed during the construction of this Bruce Banner object, which sounds weird to say because since he's a person. But when we construct a Bruce Banner object, this is a reference to the object being created. We're going to pass that to the Dr. Banner constructor. So it gets a reference to the Bruce Banner it's attached to and stores that in an instance variable so it remembers who it's attached to, which will be important for one of the next things that we'll talk about. So we have an initial state, Dr. Banner, defer to the state for all functionality, and then if the state changes, all that functionality changes because the type of the state changed. So Bruce Banner has a reference to an object of type state, which is an interface. The actual object referred to by that variable can either be Dr. Banner or the Hulk. Both of them implement state through polymorphism. They can both be stored in this variable. So we need polymorphism to make this work at all. Since they both implement state, that's a valid assignment. Dr. Banner can be assigned to that. The Hulk can be assigned to that. And each state needs a reference to Bruce Banner. That's very important, worth repeating a few times. This gets passed to Dr. Banner, so that state has a reference to the object to which it's attached. So the object, Bruce Banner here, calculator on your assignment, has a reference to its state, its current state, and its current state has a reference to it, the object to which it's attached. They have references to each other. And the last piece of this puzzle is the methods. I conveniently don't talk about make angry and calm down because I want to talk about them now, is called a state transition. So to change state, we have this extra method in the Bruce Banner class. Let me get it back on screen. This set state method, which takes a state and updates the variable. And we're going to call that method whenever we want a state transition. So if Bruce Banner is in the Dr. Banner state and somebody makes him angry, he's going to have a state transition into the Hulk state. So he's going to turn into the Hulk. So we're going to call Banner, and this is why we need this reference to Bruce Banner, the object that we're attached to. We're going to call it set state method and set its state to a new instance of the Hulk state and also pass that reference of Dr. Banner or Bruce Banner to the new state. So each state needs a reference to the object to which it's attached. We're going to pass it in the constructor by taking this reference and passing it to the constructor. After this state transition, Banner's state variable is now storing a reference to an object of type the Hulk. So then next time a method is called, maybe make angry is called again, we're going to get the Hulk implementation of that method. And in the Hulk, we call calm down and transition back to Dr. Banner to swap out all the functionality for this functionality again. So that's how we're changing between states, notably without any conditionals, but changing the behavior. If we call make angry twice, then calm down twice, we're going to get 4 different method calls because it depended on the type of the state. And that's the state pattern. That's our first state pattern example. So Bruce Banner, we created Bruce Banner. Bruce Banner is the only class that the outside world will interact with. Just like your calculator, the calculator is the only class that the GUI is going to interact with. And then it's going to call those methods, and then those methods can do all kinds of different stuff with other classes, other complexity. It's going to have a reference to a state, defer to that state for all the functionality, allow state transitions, and each state will define what those 4 methods should do, including any state transitions. And a state transition, like in your calculator class, you won't always, like here I just have straight state transitions into these methods. What you'll typically want to do is process the button press, handle that whatever you should do with that button press, and then also state transition to a different state if the buttons are going to change behavior, if the calculator should change behavior on that button press. All right, any questions at this point? Is there going to be a lot of hard coding? I still don't know how to think about that one. Yeah.
So, like for this example, we have our Banner class. Every time we go from Banner to the Hulk, we're passing through that same transition, that same Dr. Banner. But every time we go from Hulk to Dr. Banner, we're creating a new Dr. Banner output.
Mm-hmm. Yeah. So the way this code works, we're going to create a new object for the new state every state transition, which is kind of memory inefficient. It's not the best way to do it. We could get rid of that. We could reuse the states and switch back and forth between the same objects by trading out the reference and make this more efficient. But I just didn't in this case. If you don't for the calculator. So when we have a state transition, like we start off as Dr. Banner and then we switch to the Hulk, this Dr. Banner state that we were in, we don't have a reference to it anymore, and it'll end up getting garbage collected. Then when we switch back, that Hulk would get garbage collected. So yeah, it's kind of inefficient, and I'm letting the garbage collector save me here. But what we could do is apply another design pattern, the singleton pattern. In each one of these Dr. Banners, I would have a static Dr. Banner or the Hulk. Each state, I would have a static method called usually getInstance. And it's going to, the first time it's called, create a new object of type Dr. Banner and then return a reference to it, but also store that in a static class variable. And then if that's not null, just return it and then keep reusing the same one over and over again. So that's the singleton pattern. So I lied, we did get two design patterns in. I said I'd only talk about one. But that's what I would do if I was really worried about that memory efficiency. But I'm not worried about it. I actually wouldn't set up I don't want to go too much on that. Oh, actually, the clock says I better not go on that tangent. I wouldn't set it up for reasons that I don't have time to get into. All right, so this is fine. We saw what the state pattern was, but realistically, I mean, you would have a really good argument if you said, hey, Jesse, I don't want to do any of that. Like, I'm just going to have a Boolean flag that says, is the Hulk, or in the Hulk state. And for each one of those 4 methods in the Bruce Banner class, I'm going to say, if we're the Hulk, do the Hulk thing, else do the Dr. Banner thing. And forget about this whole state pattern and inheritance and polymorphism and all of that stuff. I'm not going to have those 3 extra classes. I'm just going to have a Bruce Banner class and 1 Boolean flag and done with it. right? And you'd have a pretty good argument. Like for this case, the state pattern didn't really help us at all. We really didn't see the benefits of the state pattern. But the true power of the state pattern comes in when we have more. Like if we just have 2 states, it's not that big of a deal. When we have more than 2, especially when we have lots, that's when we see the power. So enter Professor Hulk. Professor Hulk is the 3rd state that Bruce Banner can be in. And this is Bruce Banner in his Hulk form, but also with full control. He's great in a fight, and he's a world-class scientist, the best of both worlds. So how do we add Professor Hulk to our code? Well, if you're using a Boolean flag and saying, is the Hulk, then do this, else do that, you have a bit of structural change to make. You have to re-architect your code. You might change that Boolean flag to a string and have it be the Hulk, Professor Hulk, or Dr. Banner. You might add a second Boolean and then have a couple Booleans in each of your conditionals. There are ways to solve it, don't get me wrong. You can definitely do it. But then if we have like a 4th or 5th state, you're going to constantly increase the complexity of your code and the complexity of your architecture. With the state pattern, we're done with the structure. And each time we want to add a new state, it's as simple as creating a new class for that new state, implementing state, and implementing those 4 methods. What should these 4 methods do in the Professor Hulk state? And our questions are pretty easy. What should we do when he make angry, calm down? Just each method. What should he do in this state without thinking about the other 2 states while we're doing that? And then figure out our state transitions into and out of that new state. I'm going to put this method, learn control, in the Bruce Banner class. So no matter what state he's in, when he learns control, he's always going to transition to Professor Hulk, which can be useful to have methods. If a method doesn't depend on the current state, just put it right in the base class itself. And then Professor Hulk, we can't transition out of Professor Hulk in this code base. And we didn't modify any existing functionality. Our other 2 states work just the way they always did. We added the new state and transitions between the state, and that's it. Like, we're done. We just added that 3rd state with no fundamental change to our code base. We were really at the bare minimum of what's the extra functionality we want to add to this program, to this code, and that's it. And it's very helpful to have state diagrams when we're doing the state pattern. I like to see these in office hours. I like to ask for them or ask you to draw out your state pattern, is to visualize what states you have and how you transition between those states. So our initial state, Dr. Banner, call make angry, transition to the Hulk, calm down, transition back to Dr. Banner, and learn controls going to Professor Hulk, and we can't get out of Professor Hulk. Drawing these out, starting with pen and paper or whiteboard, is a good place to start for the calculator assignment. And draw this out. And then once you have your state diagram, go into the code and creating